We're going to talk about another method of approximation called the Trapezoidal Rule and Simpsons Rule. And Simpsons Rule is not on the AP exam, but I'd like you guys to get to know a little bit about Simpsons Rule, because when you hear about it in college, you won't have that, oh, I've never heard that before look in your eyes, right? You'll know exactly what it's all about. But I won't test you on Simpsons Rule without the use of your calculator, which we have a program for. So instead of adding up rectangles, we're going to add up trapezoidal areas. So we have to remember what the formula is. So let's recall what the formula is for the trapezoids, the area of a trapezoid. And that's area equals 1/2 the sum of the bases times the height. And if we were to draw a trapezoid, remember in calculus, when we draw our trapezoids are on their sides. Okay? And the left side is base 1 and the right side is base 2, because those are the two parallel sides. And the height is along the x-axis. And the height here is going to be delta x. All right, so our formula is going to be area equals delta x over 2 times base 1 plus base 2, and we're going to get these bases by using function values, function heights. Okay, so how do we figure out what delta x is if we're going to approximate the area under x squared from 1 to 5? We have a formula for delta x. It's equal to b minus a over n. Right, b minus a over the number of rectangles, but we're going to use it as the number of trapezoids. And in this case, we're approximating the integral from 1 to 5 of x squared dx. So our a is 1, our b is 5, and the number of trapezoids the problem stated already was going to be 4. So this would be 5 minus 1 over 4, which is 4 over 4, which is 1. So our delta x is 1. All right, so what we're going to do is draw trapezoids now. And with trapezoids, we're going to use the function heights on either side of our delta x here. So that's delta x, and we're going to create a trapezoid connecting the left edge and the right edge together. Unlike with rectangles, we just have the left edge, right? Or the right edge. And with trapezoids, we're going to use both. So we're going to make both, we're going to make 4 of them here. Because we're going all the way to 5 with widths of 1. Now, just based on your observation, we have 4 trapezoids. The areas are looking a lot better as an approximation, wouldn't you say, compared to LRAM and RRAM? Yes. And it would be. So let's figure out where these points are. We have 1 here because the function is x squared that we're finding the area under. And then the next point here would be 2, 4. The next height would be 3, 9, good. And then, whoops. And then 4, 16. I can't write. 4, 16. And then 5, 25. All right, so we're going to say that we're going to approximate the area under this curve, and I'm going to use a curvy equals here because it's not exact. And then delta x for each one of these trapezoids, are they all the same? Yes. So we can factor that out in front. So it would be delta x over 2 times, I'm going to make this smaller. All right, what's the first height? The first trapezoid's base 1 and base 2. It's going to be 1 plus 1 plus 4, right? Because
oh, yeah.
we can do it functionally though. You want to say f of 1 plus f of 2. That's the first trapezoidal, base 1 and base 2. Okay, what's the second one?
F of 2 plus F of 3.
Yep. I'm going to put that right up here. Okay. Plus f of 2 plus f of 3. So that's base 1 and base 2 for the second trapezoid. The third one.
F of 3 plus F.
That's right. F of 3 plus f of 4. Base 1 and base 2 for the third trapezoid. And then the last one's going to be f of 4 plus f of 5. Those are our 4 trapezoids. All right, so now we can plug in the numbers. So we know delta x, you said, was 1, so this would be 1/2. And the height at 1, we said is 1 plus 4 plus 4 plus 9, good, plus 16 plus 16 plus 25. All right, you guys get calculator happy and tell me what that is.
You want that calculation to get calculator? Oops.
We're calculating right now.
Divide by 2. Oh, divide by 2. I can divide by 2. Divide by 2, 42. Yeah.
Got 42? That sounds reasonable. 42 units squared. And of course, that's an approximation for the area under the curve. Do we recall how to do the actual? Isn't that equal to the antiderivative?
Yes.
All right, so we're finding the, how do we find the actual? We have to actually, get it? Actually take the antiderivative. So the integral from, well, let me write actual here. The actual area is going to equal the integral from 1 to 5 of x squared dx. And we find the antiderivative, which is
X cubed.
that's right, x cubed over 3, evaluated between 1 and 5. All right, so that's going to be then, I cube 5 and I get 125 over 3 minus 1 over 3, which is equal to 124 over 3. And if we do that decimally, I believe you will let me know what that is in 2 seconds.
41.3 repeated.
Yes, 41.3 repeating units squared. So how close did we get with a very small 4 trapezoids? We got 0.7.
Pretty good.
We did pretty good.
Yeah.
And it only gets better if you use more trapezoids. And what's really good about this approximation, and it's better, is because we're getting the best of both worlds, because we're using the left and the right edge. And the trapezoidal approximation, so the area using the trapezoidal method, is equal to L ram plus R ram divided by 2. So it's the average of L and R, and it makes sense because you are using the L and the R in the trapezoidal method. Okay? So let's come up with the general formula for the trapezoidal method. And I wanted to see if you noticed a pattern here.
That you use, like you have F2 like twice.
You
and
do.
F3 twice.
you have F2 twice, you have F3 twice, all the middle ones twice. And the first and the last one are only once. And that's because, what are we doing with these bases here? We are actually sharing them. The interior bases are being shared. So the first height is all by itself, and then the second height we use twice because it belongs to both the first trapezoid and the second, and vice versa, right, all along. So let's come up with the general formula. For the trapezoidal method, with, and I should put this in parentheses, with delta x uniform. Now what do I mean by that? That means they're all the same width. Okay, so we can approximate the area under the curve from A to B of f of x dx. And remember, it was the height over 2, and the height was delta x. So this will be delta x over 2 times, now we're starting at A, so the first base will be f of A plus 2 times f of A plus, how do you get to the next point?
F of A plus 1.
Not 1, but plus, I'll go back up here. F of A plus, yes, delta x gets us the next point. So this is going to be 2 f of A plus delta x. It's because we were sharing both of these. Plus 2, and I'll do one more, f of A plus, how do we get to the second one? 2. That's right, 2 delta x. Plus, and we follow the 2 pattern until the very end where we put f of B. Whoops. I put f of B. All right. And so the pattern is 1, 2, 2, 2, 2, 2, 1.
Yeah.
Okay. And this is pretty simple. It's very similar to L and R. You just have to draw them, and then you'll know which function heights to use. All right, moving right along.
This is when it gets difficult.
Never difficult.
You said this is simple, so then I was like, oh no.
Well, it is simple. Now Simpsons Rule, and I have to always say it's not named after Homer. And believe it or not, it's not named after the person that it's named after.
It's not Jessica Simpson.
No, Mr. Simpson just published it in his book first.
Oh, really?
You know? And believe it or not, we had this discussion in class that I took this from the book. It says the formula that underlies Simpsons Rule was discovered long before Simpson was born. Just as Pythagoras did not discover the Pythagorean theorem. Now everybody's head exploded when I said that.
Nobody ever told us that.
It is another of history's beautiful quirks that the ablest of mathematicians of the 18th century, that Mr. Simpson was not remembered for his successful textbook, but for a theorem that he did not, or a rule he didn't come up with. Fascinating. And we're going to talk about someone else who has a famous thing named after him. All right, and later this semester we're going to talk about another guy named L'Hopital who did not invent L'Hopital's rule, but yet we named it after him, and it was Bernoulli that discovered it. So anyway, history is not fair sometimes. All right, so this is Simpson's rule, and instead of putting nice lines above, like we were using secant lines basically for the trapezoidal method, we're instead of imagine our curve doing this. Okay, that's our curve, and then we're going to approximate it. Instead of putting on top of the curve little micro tangent lines or secant lines, we're going to put mini parabolas on top. So Simpson's rule is really helpful when you have a curve that's curvy and not linear. Because if you go back and look at the trapezoidal rule, this is a curvy curve, but we're putting the secant lines between, these points as our approximation. But if we put little parabolas on top, you see how much closer we could get perhaps to the approximation being real? So Simpsons rule, instead of, like I said, using lines, uses parabolic arches on top. And this is the formula for a parabolic arch right here. It's h over 3, where this is h, which we would call delta x, times the quantity L, which is this length, which is the left height, M, which is the middle height, and R is the right height. So this is L plus 4M plus R. Now, I am not expecting you to memorize that or even know what it is. I just want you to know that its Simpsons rule is different in that it puts what on top? Many quadratics, many parabolas on top, and it has a different formula. And since the formula is based on 2 intervals, you must have an even number of intervals in order to do this. We did with our trapezoid 4 intervals. Simpsons rule will work with 4 intervals, and they just have to be even number of intervals. All right? And what I'd love for you to do is, if you look at your calculator, and go to the apps, and Calc Tools, which is the app that I gave you. You hit the apps button, the purpley button, and then you get to Calc Tools, which if you scroll up, you'll find it. One more, there it is. Click on that, and then hit F3, the integral menu, and then you see how there's Simpsons rule right there. So click on Simpsons rule, all right, and know that we're in alpha mode when we first start this out. So clear out your function and hit alpha. All right, now type in x squared, and we're going to compare the Simpsons to the Simpsons approximation to the one that we did just a minute ago with the trapezoidals. And we're going to, what are we approximating? We're going to be approximating the integral from 1 to 5 of x squared dx. We want to know the area under that curve. And with Simpsons method, now we're going to say x squared, we're going from 1 to 5. Yep. And how many intervals did we have? We had 4. And that's an even number, so we can do that. And you press enter, and it's going to draw it for us. Let's see. There it is. What does it tell us? Well, that's from your calculator screen. It's going to give it to you in a minute. What is it? Simpsons rule says it's 123 over.
Oh, sorry, 123 over 4.
Is it,
or 124 over 3.
Oh, sorry, 124 over 3. I read it wrong. 124 over 3.
Sounds pretty exact.
Guess what? This is the same. I can't write. Goodness gracious. The same as the exact. What is really cool about that is we are approximating the area under a quadratic with an approximation technique that uses little quadratics. So it's going to be a perfect fit. Okay? So let's say you're taking a test on Tuesday. Wednesday. And hypothetically, and you had to do all of the methods. If you go to your calculator menu, again, you go F3. You have to escape, I think, a couple times to get out of there.
Oh, there we go.
Okay, now hit F3 again, and you see number 6. What does it say? Comparison. So if you press that key, comparison, and you do that same integral, go ahead, press enter.
Oh, wow.
It's going to give you all of them. All right? It's going to give you L, R, M, trapezoidal, and Simpsons approximation. So you on the calculator section. So I'm going to give you a function, and I'm going to tell you how many intervals to use, and you'll be able to use the calculator to tell me what the Simpsons rule number is, right? I mean, that's going to be really easy for you to do. So So that's all there is to it for trapezoidal rule and or trapezoidal method and Simpsons rule. All right.